All right. So, hello everyone. My name is Alexandra Mateja Novak. Thank you so much for joining us today. This is one in a series of coffee talks sponsored by the Center for Geospace Storms. And today's particular theme is going to be computers in space coffee talk. So we have three panelists here with us today. I'm going to be the moderator, the host. I'm from Johns Hopkins University Applied Physics Lab. I'm a planetary geologist here. The three people that we have on the panel today are all people who work on the project, the Center for Geospace Storms. And so this is basically scientists that are looking at a lot of space weather type science and forecasting and modeling of that space weather, and they will themselves tell you why it is so important to study space weather and how they're using computers to do it. So with that, I will go ahead and stop sharing this main slide screen that I had up, just as an introduction for when people first call in, and we can just get right into the questions. So I'm going to ask all three members of the panel the same question. We have three questions, so I'll be asking each of them three questions, and then from there we can open it up to more people at the end. We'll be done definitely by 6 o'clock, and with even extra time before 6 for more people to ask their own questions, or you can put a question in chat if you don't feel comfortable asking it yourself and you just want us to see the question and have someone answer it for you. Excuse me, please feel free to put it in the chat as well. So with that, the first question, and I'm going to mix up my order of asking people questions a little bit, but the first question I have, we'll go ahead and start with Dr. Kareem Sorathia. And please also, when you begin, please introduce yourself. I didn't put that part in the question, but that goes without saying. As you begin talking to everyone, please introduce yourself. So the first question I have is, and Dr. Sorathia, you can start. Describe your career path, what inspired you to pursue a career in space science, and how you use computers for space science.
Sure. So yeah, let me start by introducing myself. I'm Kareem Sorathia. I'm a scientist at Johns Hopkins Applied Physics Lab. And I can say a little bit more about what I do in a second after talking about my career path. So I guess the short version is that my career path was circuitous. I did my PhD in applied mathematics, with most of my PhD and postdoctoral work studying the plasma physics around black holes. And pretty shortly after starting my postdoc, I realized that the astrophysics job market was a wasteland of broken dreams, and thought to go into some other areas. I spent a few years bouncing around a little bit, but I should say that one nice thing is that being a guy who has a PhD in applied mathematics, being able to make a big computer solve a hard math problem makes it very easy to find all sorts of things to do in the world that will give you money. So I did, various other kinds of like scientific software things, some in the engineering, some in sort of atmospheric chemistry, atmospheric science, things like that, until I sort of fell into the group at Johns Hopkins doing geospace science. So it turns out there's a surprising amount of overlap between the plasma physics around black holes and the plasma physics around Earth. And I found myself a home there, doing work studying geospace, basically this plasma environment in sort of near Earth space, using these very large and complex supercomputing models. I think if you're trying to say something, you're muted.
Yeah, sorry. Thank you so much. Next, same question for you, Dr. Bao.
Hi, hi everyone. I'm Shanshan Bao from Rice University. Currently, I'm a postdoctoral research associate. My undergrad study actually is was in a completely different field. It's in nano-optics. So basically, we study the material using optical methods in the scale of 10 to the order of -9 instead of something huge in space, like something hundreds of or hundreds of Earth radii. So when I was so when I applied for graduate school, I found RISE because it's very strong in nanotechnology and nanoscience. That's why I applied for RISE. But during my fourth year in the undergrad research, I find it's less meaningful. I don't feel a sense of achievement in the nanoparticle or nanoscience research, because a lot of people just using optical methods to characterizing some nanomaterials they just manufactured, but how much science we are looking into, that's a big issue. So that's why I attend the brown bag launch meeting at RISE. That's a very good bridge for professors looking for undergraduate and graduate students who just entered their graduate study. So I met Frank during the Black Bag launch meeting, and he introduced me to the world of space science, and I started to learn the fascinating science in of the space physics. And RISE is famous for its RISE convection model, and it's a beautiful numerical model that describes the ring current particles dynamics. And I started to take courses at in solar physics as well as magnetosphere physics, and started to get my hand dirty with the models, and started to work with supercomputers at NCAR during my graduate research. At the end of my graduate study, I started to know the new generation of MHD model, which Kareem developed, and I find their vision is very inspiring in the aim to unify a different area of the geospace and make a very sophisticated model that could capture different dynamics in the geospace, and that made me to stay in the area and continue my research and the model development work in this area. So for the usage of computers, basically I use Python to do some plotting, as well as some software for visualization. And for coding, we use Fortran as a language, because it has some advantages in the computing speed, and I think it's also a legacy to follow, because a lot of physicists use Fortran to write numerical codes. Yeah, basically that's what I have now.
Excellent, thank you. And yeah, there will be an opportunity in the next question to go a little bit more into your science and why it's important, but that is a great introduction. Thank you. Dr. Kevin Pham, you're next. So describe your career path, what inspired you to pursue a career in space, and how you use computers in space science.
All right, so I guess start off quick introductions. I'm Kevin Pham, a project scientist at the National Center for Atmospheric Research in Boulder. So how I landed here, so I started off my undergraduate with math and physics. I did math because I was just like, hey, it's something that you do as a physicist anyway, so I just picked up a math degree for fun. And as far as specific fields, I was just kind of swimming around, and I would talk to every professor as an undergraduate and be like, hey, what do you do? oh, that doesn't sound interesting. I'll go talk to somebody else. And professors just didn't really care. So I just went, asked everybody. And at the time I was deciding between astrophysics, space physics, high energy particle physics. A lot of that sounded interesting, but I just talked with everybody. I got involved on a bunch of projects, and as an undergraduate, the project I got involved the most with was high energy particle physics. And I found out that I did not like it very much. So when I joined I went to University of Texas at Arlington for graduate school, and so then I decided, okay, I'm going to stick somewhere in space rather than look at particles. And then, with space, there was astrophysics and space science. And similar to Kareem, I found out that there's not a whole lot of a future in astrophysics. I went to the professor and I asked him, all right, so first thing I want to know is, what do you do? Do you spend all your time coding? Do you spend all your time doing very complex math problems? What exactly do you do? And to decide if that's what I want to do in the future. I'm okay with working on some math problems, but I prefer to work on computers over doing math problems. And then the other thing I asked was, once I graduate under you, what do I do then? And the astrophysics professor was, well, you can either do more astrophysics and never verify your work, because unless you're alive like 10 million years from now or 10 billion years from now, then you might be able to verify what you've come up with. Otherwise, you're not going to see it within your lifetime. Or you can go work for some random company like Google. I'm like, oh, well, I kind of don't. If I wanted to do that, I would have gone into computer science or something. And then when I went and talked with my advisor in space science, he was like, well, you can go work for companies like Raytheon or Lockheed and continue doing space sciences with them. Or you can continue doing space science on recently launched satellites. I'm like, oh, that sounds a lot more real time. And, you can see things happening and evolving within my lifetime. And that sounded a lot more exciting to me. So that's how I ended up with that career path. And then how I got at NCAR, when I graduated, I ended up working in a slightly different field in radiation belt. I started off doing magnetosphere things, and then I moved to the radiation belt, and then I ended up finding out that magnetosphere was a lot more interesting than the radiation belt. So I went back into the magnetosphere after I jumped around a little bit. And then so that's when NCAR grabbed me, and I'm still here now. As far as what I use computers for, I use computers to solve a lot of things. Solve computer simulation models like what Kareem and Shanshan was talking about, using it to plot things. I also use Fortran a lot, because I've been finding, if you try to download a program that somebody else did, and you go, oh, I want to make a plot of this this variable, and then I want to divide the variable by 5. It might not be the easiest thing to do. I could easily just code that up in Fortran in 30 minutes and have it do it for me, and then use the computer that way, rather than try to find somebody to do it for me, or find the correct program to do that. It's not easy.
Excellent, thank you. And I really appreciate in your response how you talked about you went around and you asked what people are doing to look for something that was interesting to you. And I think that's really good advice. Sometimes you just have to see what's out there, because you might not actually know what opportunities or what fields of study exist out there. And it takes talking and asking to people. So thank you for mentioning that. All right, so for our next question, we're going to get a little bit more into the science. And if any of you have any slides that you want to share for this response, just let me know and I can share hosting capabilities with you. So for this one, we'll go ahead and start with Dr. Shanshan Bao. So please explain why what you're doing is important and why we should care. And did you have slides that you wanted to share?
Yeah, I have 2
Okay.
simple slides. Yeah.
Okay, I just made you a co-host, so you should be able to do that now.
Okay. Can you see my screen?
Yes, thank you.
Yeah, so here I'm showing on the left is a illustration of a contrast of the Mars today, and what it may have looked like a billion years ago. We all know that Mars right now is not uninhabitable, so there's not plenty of atmosphere there, and no water, no liquid water there right now. And so scientists think it is due to the sudden a sudden loss of its magnetic dynamo, causing there's no strong magnetic field on the planet. And you can compare on the right the magnetosphere of Mars and the Earth. They look quite different. And for the Earth, we can see there's a dipole in the inner outer shell that can effectively deflect the solar wind, and the magnetopods and all the field lines can protect the Earth's atmosphere from getting blown away by the solar wind. On the contrary, on the Mars, the magnetic field there is very weak, and it's not showing a dipole structure, and it's just some random field line from the surface, and you can see the bow shock is very close to its ionosphere, which will cause a loss of atmosphere molecules and make it when there's no atmosphere, it is hard for living things to live there. So that's why I think it's very important for like human beings to have a magnetosphere there. And even though we have this magnetosphere that protecting us from loss of atmosphere particle or molecules, we're still facing a lot of issues when there's for example, solar storm happen. So those charged particles will cause a bunch of issues in the satellites in space. For example, there will be energetic charged particles that causing GPS failure or causing charging effect for the satellites. And also, I guess everyone know the news. There's a loss of SpaceX lost their 40 satellites because of the atmosphere dragging effect from the solar storm. And also during a strong geomagnetic storm, there will be induced effect like causing geomagnetic induced currents in power grids, and also causing strong currents in the cables, and that will cause a lot of money and damage to the infrastructure of like our human beings. So I think it's very important to know those effects and study it, know what is causing it, what's the drivers of it, and how to predict and forecast for those situations. So I think that's why space physics or space weather is very important.
Thank you so much. That was great. And if you have any questions, please, we'll get to them at the end. So next, same question for Dr. Kevin Pham. We'll have you go next. And I think I also have to make you a co-host.
All right.
So it should work for you now.
All right, so what I mostly do is I mostly look at the interaction or the coupling between different geospace regions. And so Up here on the top left is the magnetosphere, which is the upper edge of the Earth's atmosphere, and you can see the Earth atmosphere and all the different layers seen below. Usually, if you're in meteorology, you might go up to the troposphere, stratosphere, and sometimes the mesosphere. And then there's the thermosphere, ionosphere, and a lot of that is coupled out, that keeps on going, and eventually you reach up to the magnetosphere above. And so what I mostly do is I look at how things from above affect things below, and how things below propagate back up to the top. And some things that kind of cross the different regions in geospace between a magnetosphere and Earth is, like, for example, you see here in the top middle here is a total solar eclipse. When you have a total solar eclipse, this giant shadow goes through, and that really affects pretty much the entire atmospheric column. And how that affects the rest of the magnetosphere, we don't really have a good understanding of what happens, and that's kind of what I've been looking at. Other things that I've been looking at is in the top right here. Well, I'll talk to you about top right in a second. So then the bottom here is the surface pressure. This is the pressure that you feel at the surface, and this is the change in pressure. So you can see there's a giant blob down here in the southern hemisphere. This is actually the Tonga volcano exploding last year. And so when that thing explodes, you can see that it launches a gigantic surface pressure wave that propagates away, and just moves around the entire globe. But this is the surface pressure. If you take a look at the electron column density, which is the amount of electrons in the entire column, you can see that this thing is huge. It's really fast, but it's really large and affects the entire atmospheric column. And how that gets, what that does to the magnetosphere, we don't really have a good understanding of that. And, these are things that I look at. Other things that I do is, not just looking at the electromagnetic of things going up and down and moving the whole column. You also have a lot of mass, a lot of particles, and a lot of oxygen, hydrogen, and a lot of things from the Earth's atmosphere that flows out into space, especially in the polar cap region here. So within the aurora, you can see all of this blue color coming out of the aurora and getting into the rest of the magnetosphere. And that's shown over here on the right side, where you have an ozone depletion in the pole. That affects the F layer ionosphere, and then a lot of those particles kind of move up and then gets out into the magnetosphere along these magnetic field lines. So that's pretty much what I've been working with.
Excellent, thank you. And lastly, we'll have Dr. Kareem Sorathia. Did you have slides that you also wanted to share? Oh, you're already doing it. Okay, great.
Yeah, so what I'm showing here is actually, this is a, let's see, did I not, this is a video? Oh, I guess not. Let's see. Oh, well, I'm going to show it this way, but basically this is showing a video from the Hayden Planetarium, which is sort of illustrating the interaction between the sun and the Earth. We have the sort of solar wind, which is this stream of plasma being blown out by the sun, interacting with the Earth's magnetic field, which you can sort of see here in yellow. And so here, I have the picture of the sun being very nice and happy, but that's not always the case. Sometimes we get these very massive expulsions of plasma coming out of the sun called these coronal mass ejections, and these cause geomagnetic storms at Earth. And so one of the reasons why, you should care about this is because it really affects what's happening in space, and space is where we keep our stuff. This is showing here each of these green dots is actually an individual satellite that we have in near Earth space. And when we see these massive geomagnetic storms, these can endanger, like Shanshan pointed out, these endanger those satellites. And even further, it can sort of affect the power grid. It affects these underwater lines. So what happens in space can cause a great deal of damage and influence what's happening on Earth. So, that's one important reason to care about that. Of course, I'd be lying if I said that's the reason I care about that. It's an important thing, and it's certainly important to understand and do, but also just for my main interest in this is just scientific. Like, it's fascinating to understand all these different ways in which the things that can happen right above our head, like the aurora, are really being driven by things that are happening very deep in space, and how those two systems interact in these very intricate and complex ways. And to understand that, you really need these very, very massive supercomputer models that require knowing how to have these, some of the most powerful supercomputers on the planet solve these difficult math problems that also, of course, involves taking all of these complex physical and scientific interactions that happen between systems like the atmosphere and the magnetosphere and the sun, and codify them in math that we can then figure out how to solve on those big computers. And so that whole series of sort of interactions of putting that all together is something that's always just been very fascinating to me personally.
Excellent. Thank you all. Those are really, really good overviews of what you're doing and why it's important and why we should care. So next question is a little bit more giving advice and ideas of how some of our callers, or not callers, but people who are connected with us today can also get into the fields that you're in, the fields of study. And Dr. Pham, you actually alluded to this a bit in your an introduction answering to the first question. So we'll go ahead and start with you. Can you imagine ways in which an undergraduate student could be involved in the kind of work that you do? What resources and opportunities do you take advantage of as an undergraduate?
So as an undergraduate, I didn't take, besides taking advantage of nearby professors and just bugging them until they give me a project, I didn't take advantage of too many other resources. Once I'm now working at NCAR, there's a lot of resources now. So there's like a source program that we have that will send you to us for the summer. There's a lot of REUs that you can join. There's a lot of programs that I'm involved with, and I do work with undergraduates fairly often. A lot of ways that undergraduates get involved is to do, for example, I'll run really big simulations, and then I'll find simulations are in 3 dimensions and very complex system, and I'll find some sort of feature that might be that might stick out within the simulation, and then undergraduates can look through a lot of satellite data that exists, a lot of data that exists out there, and look for these features and try to verify what I've done. And you can either do that by hand, by looking at through satellite data by hand and looking at plots, or you can, if you want to be more fancy about it, you can try to write a Fortran program that will run through all of the data, or Python if you want to do Python. Then you can run, that will look through all of the different satellite data and try to find these features that I have that I found in the data. And then other things that the other things would be I can give you some data, and then you can try to visualize and learn how to visualize and rotate through the magnetosphere and try to figure out, I'm looking for this pocket of density, try to find that somewhere in the magnetosphere and what that looks like and what their features are. So there's a lot of opportunities for undergraduates to get involved with space science.
Great, thank you. And just as a reminder, what you said at the beginning, bug your professors, talk to your professors, find out what they're doing, and look for something that interests you as well. And it's okay to talk to a bunch of different people to figure that out. That's what I did as well. So that's perfectly normal to keep talking to somebody until you find something you can connect to. Next, Dr. Kareem Sorathia, if you would also answer that question. Can you imagine ways in which undergraduate students can be involved in the kind of work that you do, and what resources they could take advantage of?
Yeah, and I mean, so to echo that point again, just taking advantage of all of the great opportunities to work with researchers that you have. Throughout my even high school and then college, I worked in lots of different research labs with different professors, all sorts of kinds. It took me a long time to figure out what area of research I wanted to do, but very early on, I realized I just loved working in those environments, where you can just think about these tough problems and find different ways to solve them. It doesn't matter what they are. You very likely don't even know which one you really will like, because it's difficult to know what research is actually like in a different field just based on what you learned in your first undergraduate class. And so getting into those environments and testing out the different things you might be interested in is great. And not only that too, but no matter what you end up deciding to do, you just learn so many useful skills. To go back to what the kinds of things that we have is, we have these massive supercomputer simulations that just, at the end of the day, produce trillions of numbers that we then need to figure out what to learn from. And this basic problem of turning just massive amounts of data into understanding, like intuition, like knowledge, is a very difficult problem. And learning how to deal with that is a great thing to just do, is a great thing to sort of have experience with, no matter what field you end up going into. And so being able to work with data analytics, data visualization, telling stories with data, how to interpret data, these are exactly the kinds of things that we have to do with the things that we work with, but are useful no matter what you end up doing. Like using mathematical tools to understand massive data is just a very useful thing to be able to do.
Thank you. And finally, Dr. Bao.
Yeah, I want to mention that actually there are a lot of great seminars held by different departments, and also there are joint seminars held by different universities. And actually, this is a very good opportunity for undergrad students to reach out to different fields and to see what scientific topics people are studying. And through the process, you may think, oh, it's kind of overwhelmed because that's some research work done by established research scientists. But it's a good way to broaden your horizon and to see what kind of research people have been doing. And with some of them you may find it's very interesting. That may give you an opportunity to reach out. For example, you can talk to the speakers, or you can talk to the professor that giving the talk, and you can reach out to let you to attend their group meetings if possible. And the other way I can think of is that, for example, if you're taking a computational physics course or applied math course, you have you will learn numerical methods to do simulations or modeling. And here you can choose some topic or subject to study that is related to the space science. For example, my first simulation work or modeling work is to do a test particle simulation to simulate its bounce and drift motion in a dipole field. That's a easy thing to do, and it's very interesting to do, and it gives you a good sense of achievement when you see your particle that is bouncing and drifting along the way. So I think start with a simple project and get your hand dirty to projects, and that's my suggestion.
Fantastic, great, thank you. And yeah, that just to add to that, professors, they are oftentimes looking for help with things that they can sort of help teach you some new skills. And maybe if you don't get into that field, that's okay. Those are skills that you can take over to wherever you end up. So it is really important to volunteer yourself to help with the professors in your department with any kind of work that they're doing. It will all be beneficial in your experience. So with that, thank you so much to our panel. You answered the questions very well, and these were, questions that you had ahead of time, so you were able to prepare for them a little bit. But are there any questions out there from the audience? Again, you can feel free to ask yourself if you want to unmute yourself, or if you prefer to put it in the chat and one of us can ask it for you, that's fine as well. Well, I had a question. Some of you, and whoever wants to take this can take this. Looking at space weather versus weather here on Earth, we saw some influence in the atmosphere, the very high level atmosphere from a recent volcanic eruption. What about the hurricane that just went through Florida? Is there any effects in upper atmosphere to natural weather events such as that, in addition to large volcanic eruptions?
Yeah, that's a really good question. The answer is that we don't know. That's a lot of these things is brand new. Computers have only recently gotten good enough to really combine a lot of these models together and really the expertise is only starting to be there as well, because you need somebody who's good at both terrestrial weather or knows a little bit about terrestrial weather as well as knows a little bit about the magnetosphere to kind of connect them together and to look at what happens when you put a hurricane in there. And that's something that we don't know. We'll try it, but that capability is not available yet. Hopefully we'll have that capability soon, but we're still working on that.
That is often the answer to some of these questions is, well, we don't quite have that capability yet, but maybe one day someone in the audience will get that figured out. Any other questions from anybody else? Sava, I saw that you joined us. Did you have any words for everybody? Sava Merkin is the PI of the CGS program, the Center for Geospace Storms. Sava, can you hear me?
Yes, I can hear you.
Okay.
I'm far away, 6 hours in front of you guys.
Oh, okay.
So just great to see everybody, and it's you know, great seeing you guys giving your sort of snapshots of your career, and I hope that folks will follow suit.
All right, thank you so much. Yeah, if you're many hours ahead of us, it sounds like it's pretty much bedtime for you right now if you're that many hours ahead. So thank you for calling in anyways. So yeah, if anybody has any other questions, you can reach us through emails, and let's see, our emails are available on the CGS website. So if you go to cgs.jhuapl.edu, all of our team's emails are listed under the team section of that website. So feel free to reach out to us if you have any questions. And also for all the universities that are involved, again, you can go to the team website. Thank you, Dr. Sorathia, for putting that in. If you have any questions about internships or other types of opportunities for students, please reach out to us. You can go to any of our institutions' websites, and it's pretty easy to find internships that are available, especially at APL. I'll just plug APL because I'm there right now. But APL has a really big college internship program. And what's really nice about it is once they train you as an intern, a lot of times there's even permanent employment opportunities available, because once we've invested the time to train you as an intern, many times if you do well here and it's a good fit, we'd like to see you come back as a full-time employee. So a lot of these internship opportunities are just the first step in your career path. So definitely take advantage of those, and don't be afraid to ask around and see what else other people are doing, because sometimes that's how you find the really cool projects, is you actually have to go out and look for them and find out who else is working on cool stuff and if you can help as well. So yeah, I think that pretty much concludes, unless does anybody in our panel have any last thing they wanted to say that they didn't get a chance to say during the panel interview?
I mean, I'll just say one last quick thing myself, in terms of, I think one great thing I've learned, certainly sort of bouncing around a couple of different areas, including sort of studying black holes, is one thing I love about this field is it's a fantastic way of sort of combining really fascinating fundamental science with things that also just are really important to understand for just human society, to understand these things and understand why they happen, when they happen, and things like that. And so pragmatically, it means it's a science that does actually get some money because people care if the power grid goes down. But it's also, and it's a great way to just have that opportunity to do fundamental science, not just at a university, but at different labs, through the government, through through private companies as well. So there's just a lot of vibrant and important research that gets done here.
Yeah, I have two comments. The first comment is, just let your professors know if there's anything that you're particularly interested in. It doesn't have to be in terms of science. It's just your specific skill. So my graduate advisor knew very little about coding and running the computers, but I I've always liked working on computers, and I would build my own computer, my own gaming computer, way back. And so I had some interest in that. So I told him, hey, I'm pretty good with computers. Is there anything I can do? And he's like, oh, well, let's build a local supercomputer. Here's a whole bunch of money. Go work on it. And so that's how I got into, more into computing. And then my second comment is, really don't be afraid to say and talk to your professors, even as a graduate student, what you want to do. So there was a graduate student that I was recently working with, and he did some really good work on the computer, but he was like, I have an engineering background. I really want to work with satellites. I like instrumentation and satellites. So he talked with his professor at Dartmouth, and his professor knew another professor who got money to build small CubeSats. And so the student ended up transferring to that department, and now he's building CubeSats. I think he's the lead of 3 CubeSats that will launch within the next 2 or 3 years. So just don't be afraid to let your professors know, even if you're already halfway through a project. Just let them know what you're interested in, what skills you want to use, and what interests you. So that you're not stuck doing something you don't like.
Yeah, and for comments for go back to the topic computer in science. So so some graduate student may not learn a certain language, for example, Python or C++ or Fortran, and I highly recommend you learn it not by a textbook, but by doing a project. So you can, when you meet with questions or don't know how to do it, just use Google, and that's the best textbook I know. And also try to get involved or work with like some computer guru that is better than you, and you will learn a lot from them. So Kareem is my computer guru in that area. Instead of answer me questions, he asked me how to solve a problem on my own. So that's a very good way of learning and solving problems. So a lot of when you meet with questions, you can Google it yourself and do some tests. And if you still cannot figure that out, then ask someone that's better than you. That's a learning curve, and you will benefit a lot from it.
Excellent, thank you. Yeah, and don't be afraid to ask for help, right? We've all had to ask for help, even
in the chat too.
Oh, there's okay, great. Reed George, you have a question.
Yes, I'm an undergrad student at Virginia Tech, and I'm an aerospace engineering major, and I was wondering what my next step should be after hopefully getting some undergrad research into choosing a graduate program and where that should be.
So which specific program you'd be interested in, or sort of just how to go about that in general? Just to say really quickly, having that kind of undergraduate research experience means you can get great letters of recommendation. You're much more likely to get great fellowships to pay you a stipend and salary while you're in grad school. Just having that immediately already gives you such a stronger application to go to the grad schools or the programs that you're most interested in.
Thank you.
And talk to your current professors about, what research is going on at what institutions that you might be interested in. Again, sometimes Google is great, right? Sometimes it's just a matter of searching up schools that you're interested in and looking at their programs and seeing, are they actually doing things that I'm interested in? And don't be afraid to reach out to those researchers at those institutions and create a connection with them right away, because it's good for them to know that you're so interested that you would take initiative to come find them. That's how interested you are in the work that they're doing.
Yeah,
so
I would also say just really, you definitely don't want to just look at the reputation of a school overall as the only criteria. Talking to specific researchers in the program that you might be interested in working on. At the same time, of course, you want to be careful about only going to a school for one specific professor you want to work with, because people move around a lot. But finding the right program with lots of people doing the kind of research you're most interested in is the best choice. And by doing these kinds of undergraduate experiences, you have a much better sense what kind of research you're going to be interested in before you even make those decisions.
Yeah, and to kind of echo that, a lot of fields span multiple fields. So for example, even though we say space science and space physics, it incorporates, depending on which university, we might be in the physics department, which would do more, say on the data analysis side, or you can be in the engineering department, like aerospace engineering. Like for example, CU Boulder is it's a mix of aerospace engineering and physics. And so if you're in the aerospace engineering department, you would work more on the actual satellite hardware than you would on, say, simulations or something like that. And so even if there's a field and topic you like, there's a lot of opportunities within that to kind of find what interests you the most and what you like to do.
Thank you.
Any other questions? All right, well, I think this is a good time to go ahead and end the panel. Thank you so much to everyone who called in, and thank you especially to our panelists. Yes, so everybody do their little hand clap for our panelists. This was great, and hopefully, we imparted some good knowledge onto you, especially undergraduate students who are interested in taking that next step in your science career. And again, if you have any questions, don't hesitate to reach out to us, email us. We're here to help. We want to see more scientists come into our field, and we're here to help facilitate that. So I did record this, so if there's anything that you felt like you didn't really hear quite well enough and you want to go back and listen to it again, we will be posting this to the CGS website in the next few days. So yeah, keep visiting the website for updates, and hopefully if you want to call into the next panel, we'll have a whole nother different group of panelists talking, so you can get different perspectives from them as well. So please, everyone, enjoy the rest of your evening and the weekend coming up. If you're on the East Coast, try to stay dry, but otherwise enjoy the lovely weekend that in other parts of the country that will be here. And thanks, everyone. Bye.
Thank you.
See you.